And the next talk will be a remote one, so hopefully we can queue that up. And this talk will be on automatically generating optimizations.
Hello, can you hear me?
Yep, we can hear you, and you can go ahead and take it away.
All right, thank you. Hello, everyone. My name is Abdul Rafae Noor, and today I'll be presenting our work titled MISAAL, Synthesis-Based Automatic Generation of Efficient and Retargetable Semantics-Driven Optimizations. The compiler community has long aimed for greater automation, ideally driven by target ISA and input language semantics, to generate compilers and compiler components. Recent advances in program synthesis, term rewriting systems, auto-tuning, and machine learning frameworks have started to make this possible. These tools and techniques enable compiler writers to express many compilation tasks as optimization problems, enabling high automation. While this is a non-exhaustive list, the point remains that there are many tools and techniques for reasoning about various compiler construction tasks which are being explored in research. Some benefits of why one may want to automate compiler construction tasks are: these are more scalable than human-based approaches, they can identify non-obvious results, they can reason about complex optimization spaces, they tend to be less error-prone, and sometimes even formally verifiable. Finally, these approaches lend themselves to be highly maintainable, such that as the constraints of the compiler changes, these can adapt accordingly. There have been many works which aim to automate various compiler tasks. The tools and techniques are suited for some tasks more than others. In this work, we primarily focus on the problem of instruction selection and superoptimization. There have been many recent works which have addressed this task in different ways and under different constraints. Here, we create a plot with two axes. The vertical axis describes the compilation time when using these tools, which can range anywhere from a few seconds to tens of hours. The horizontal axis describes the size and complexity of the target instruction set. There are tools which support a small subset of operations, all the way to large ISAs with thousands of instructions and in-register data reordering instructions referred to as data swizzling instructions, which are increasingly prevalent in modern instruction sets. As such, we propose MISAAL. The MISAAL work is situated in the bottom right corner in this space. We want the performance and flexibility of synthesis-based tools, but to compile in seconds and not hours. Additionally, the compilation should be lightweight so that these tools can be used on a variety of systems. The way we achieve this is by using a semantics-driven approach to scale synthesis, which we'll present in this work. In this context, our contributions are as follows. First, we propose a novel synthesis methodology that enables deriving retargetable rewrite rules automatically by exploiting similarity, but not necessarily equivalence, in the semantics of the target ISA or front-end IR. This affords us scalability both in the sizes of the ISAs which can be considered, as well as the target sequence lengths. Next, we provide systematic support for a special class of modern vector instruction sets, which require reasoning about complex in-register data movements in addition to computational instructions. Finally, we perform additional transformations to generate higher-order abstracted rewrite rules, which fold multiple concrete rewrites into a single higher-order rewrite rule. This significantly reduces the number of rewrite rules which need to be emitted. At a high level, MISAAL operates in two phases. There is an offline phase to enumerate programs and synthesize rewrite rules on the front-end IR and target ISA. Then, during compilation, a term rewriting system applies these rewrite rules to compile the programs into the target architecture. Simply moving the synthesis offline is not sufficient due to the sizes of the ISAs involved. This makes enumeration infeasible even offline. For example, enumerating x86 expressions to a depth of 2 already exceeds 10 to the power of 12 terms. Targeting rewrite rules with swizzle instructions requires going even deeper to expression trees with depths of 3 to 4. Then there are challenges with the number of rewrite rules and how to apply these rewrite rules to get good performance. MISAAL builds on top of our previous program synthesis-based HYDRIDE compiler infrastructure published last year in AS+ of 2024. As with MISAAL, HYDRIDE operates in two phases. In an offline phase, HYDRIDE consumes ISA pseudocode in vendor-specific format and automatically parses and converts them into a formal semantics which can be used with program synthesis. It also uses these semantics to automatically create a target-agnostic intermediate representation, which folds in many similar instructions across the target ISAs under a unified IR. For example, here are 3 different dot product-like instructions in Qualcomm's Hexagon, x86, and ARM described in their respective vendor-specific pseudocode. These instructions perform similar computations but are not equivalent. HYDRIDE uses these semantics to automatically create a higher order IR operation for dot product and other operations with additional parameters. We call this generated IR AutoLVM IR. Specific parameterizations of this operation represents each of the dot product instructions shown here. Here we illustrate the compiler construction flow in MISAAL. It consumes the AutoLVM IR representation synthesized by IR and constructs abstracted rewrite rules on the target ISAs and front-end IR, Halide IR in this case, to be applied during compilation. We'll expand upon this diagram shortly. So let's look at the problem of generating rewrite rules offline. Here we show 3 different rewrite rules for x86 dot product instructions with their corresponding Halide IR operations. If you see figure A, it shows a 256-bit dot product on 16-bit elements. If you try to discover this rewrite rule using naive enumeration, not only would you have to get the right sequence of operations and correct intermediate vector sizes, you would also have to use the correct variants of operations such as sign extending 16-bit to 32 instead of 8 to 16, for example. This makes enumeration difficult. Coming back to the 3 rewrite rules shown, it just feels like there's a lot of redundancy in this form of enumeration. A and B are doing similar computations on different vector sizes, whereas B and C are doing computations on different vector sizes but doing different forms of accumulation, saturating versus regular. These expressions look similar, but they're not equivalent. We could try to fold in these cases manually, but that would be infeasible due to the sizes of the ISAs involved, and it would be highly error-prone. We approached this enumeration problem by using enumeration with AutoLVM IR. Expression with similar semantics as defined by the AutoLVM IR need to be only enumerated once. If you look at the left-hand side IR and right-hand side IR expressions below, the left-hand side IR captures all 3 of the dot product instructions with the same IR operation, and similarly with the right-hand side IR due to the additional parameterizations. Using the AutoLVM IR representation is beneficial because it is highly compact. If we look at x86 specifically, the AutoLVM IR representation folds over 2,000 instructions into just 136 AutoLVM IR equivalence classes. Enumerating using AutoLVM IR is great, but it leaves us with another problem. How do we know what parameters to use? The answer is program synthesis. To define the synthesis problem, we need to define 2 functions. The first is the abstraction function. The abstraction function takes an expression in terms of the target ISA operations or Halide IR and returns its single AutoLVM IR representation with symbolic parameters. Conversely, we have the concretization function, which takes an expression in terms of the AutoLVM IR operation and returns a set of concretely parameterized expressions corresponding to specific target ISA or Halide IR operations. As you can see, a single AutoLVM IR expression corresponds to a set of multiple concrete programs. With this in mind, we can now define the left-hand side IR and right-hand side IR to be a valid rewrite rule template if there exists some concretization L of the left-hand side IR and some concretization R of the right-hand side, for which L and R are equivalent. We denote this type of equivalence with the equivalence _IR symbol. This problem can be solved efficiently as a syntax-guided synthesis problem where the syntax is defined using a concretization grammar. This also reduces the number of terms that we need to enumerate with a factor reduction of the cardinalities of the left-hand side IR and right-hand side IR concretization sets. So, the better HYDRIDE is able to fold instructions into the AutoLVM IR, the larger reduction in the number of enumerated terms. Finally, we said that this rewrite rule would be a valid template. We'll show later we can use this template to mine for valid concretizations efficiently as well as separately from this enumeration. Here we show the concretization grammar for the dot product instructions in D. The LHS IR here is the AutoLVM.dot product instruction, and the right-hand side IR is a grammar with the same structure as the above 3 Halide expressions, but with symbolic choices for the variants of the concretizations. Note that even the combination of the leaves is expressed as a symbolic choice, so the synthesis problem also solves for aligning the terminals correctly in the left-hand side and right-hand side. Once we've enumerated using the AutoLVM IR and obtained a set of valid rewrite rule templates, we can mine those templates for valid concretization separately. This is done using the same concretization synthesis problem, but with additional constraints to force either some specific vector sizes or operation variant. Because these concretizations are extracted from the same AutoLVM IR template, we can similarly create an abstracted rewrite rule which represents all of the concretizations using symbolic parameters. For example, A and B on the left-hand side describe concrete rewrite rules on vector addition with 256-bit vectors, which can be done using slicing and concatenation. As you can imagine, this rewrite rule would have many different valid concretizations for different vector sizes. MISAAL uses program synthesis to replace the numeric parameters with symbolic expressions which fit across the valid concretizations, enabling using a single higher order rewrite rule which represents multiple concrete rewrite rules. Our workflow diagram now is partially expanded to include these steps. Now, let's now turn to the problem of supporting in-register data movement instructions, or swizzles. Generating rewrite rules with swizzles introduces various challenges. To illustrate the complexity, we show that data swizzling required in x86 to target the dot product instruction. There is no single instruction in x86 which does this complex data movement, but rather, simpler data swizzling instructions need to be stitched together to produce a complex swizzle. Trying to directly generate rewrite rules with swizzles and computation is infeasible. As such, prior work with the rewrite rules does not support swizzles. Prior work with synthesis uses various heuristics to support swizzles. These heuristics involve manually analyzing the ISA and creating a complex swizzling instruction, synthesizing in terms of that instruction, and then lowering it separately. This approach makes it feasible to target swizzles but has many drawbacks. First, it requires expert understanding of the ISAs. It's limited to a set of specialized swizzles. There's limited portability for when you want to support a new target architecture, and it's limited to reasoning about a small window of operations. MISAAL uses a more systematic and automated approach by using the semantics of the ISAs themselves. The existing ISA pseudocode provides a lot of rich information in addition to just the computation semantics. Importantly, we can also analyze the data access patterns in the semantics to automatically create the complex swizzling instructions needed. In this example, we show a simplified version of HVX's widening multiply instruction operating on 4-element vectors. The operands are sign extended in order, but after multiplication, they are written to the output register in an interleaved manner as shown. So to use this instruction with ordered data, we would need to reorder the vector elements so that the final result after using this instruction is in order. The question, however, is what are these corrective swizzles? There are two possible and equally valid possibilities of these corrective swizzles. First, you could either interleave the operands before doing the sign extension, or you could do a de-interleaving swizzle after the widening multiply but before the accumulation. Both of these swizzles are derived automatically, and MISAAL creates specialized swizzling instructions with semantics for both of these variants. Since we have the semantics of these automatically generated swizzles, we can abstract them to the AutoLVM IR as well. The AutoLVM IR of these swizzles themselves are parameterized to support complex swizzling. The added swizzling AutoLVM IR classes do not increase the size of the enumeration set by a lot. The table shows that the number of concrete swizzle MISAAL finds by analyzing the semantics of the target architectures and the size of the AutoLVM IR. There is a significant reduction in the sizes of the swizzles. This is because of the many variants within the ISAs for different vector register sizes and element bit widths, as well as operations which do different computations but have similar data access patterns. We've now added another step of generating swizzling patterns from the target ISA semantics and abstracting them into the AutoLVM IR. The enumeration and pattern abstraction consequently includes the swizzling operations when generating the abstracted rewrite rules. Enumeration at larger depths becomes infeasible even when using AutoLVM IR. If we wanted to find rewrite rules at larger depths, some form of pruning is necessary, but how? As with the previously described problems, we again turn to the semantics for the rescue. Rather than enumerating all operations with respect to each other, we only want to enumerate operations with each other if they are semantically related. We define semantically related as A is semantically related to B if A can represent either partially or fully the semantics of B. This intuition is nice, but formalizing this has many challenges. For example, the semantics of two operations may be related only if the data are swizzled in a particular layout. The details of these challenges and how MISAAL addresses these using semantics are described in the paper. After this step, we have possibly overlapping sets of AutoLVM IR operations to enumerate jointly. The full offline compilation flow in MISAAL to generate abstracted rewrite rules is shown here with the phases discussed. Then in an online compilation phase, the rewrite rules are used in an equality saturation based term rewriting system to compile and optimize the Halide application program. We use egglog as our mechanism to apply equality saturation, and the details of which are described in the paper. We evaluate MISAAL across 3 production target architectures, including x86, HVX, and ARM. These ISAs spans over thousands of instructions, demonstrating the scalability of MISAAL to real-world ISAs. For comparison, we use the state-of-the-art synthesis-based compiler HYDRIDE, which performs synthesis online, as well as Halide's target-specific backends for said target architectures. Our evaluation covers 33 kernel benchmarks from image processing and deep learning. Finally, we evaluate on the following metrics: performance, compilation time, and memory consumption. With regards to synthesizing rewrite rules, MISAAL is able to identify tens of thousands of concrete rewrite rules. The rule abstraction mechanism in MISAAL then successfully reduces these rewrite rules by a factor of around 19x. With regards to performance, MISAAL also achieves competitive performance with both the manually optimized Halide IR backends as well as the synthesis-based HYDRIDE compilation. This demonstrates that MISAAL can achieve the performance of synthesis-based tools while addressing key practical challenges such as memory usage and compilation times, which prevents synthesis-based tools from being used in practice. In conclusion, I presented our work MISAAL. MISAAL uses a novel synthesis methodology using instruction semantic similarity to scale synthesis. It also performs various analysis on the instruction semantics to generate swizzling instructions automatically, which are essential for modern instruction sets. MISAAL uses these analyses to synthesize and abstract rewrite rules, which fold multiple concrete rewrite rules into a single higher-order rewrite. The use of semantics to guide compiler construction tasks is becoming an increasingly important area of research, and I look forward to many more works in this area. Thank you for attending my presentation.
All right, thank you to the speaker. Questions? Looks like we have one in the back, and while we get there, I have a quick question. So it seems like there's a trade-off when you're using auto LLVM to kind of collapse instructions into one. Is there a way to expose to the user like how aggressive to be with collapsing instructions, or is that just kind of handled by the system and the user has no way of configuring how aggressive the collapsing is?
So yeah, right now we have, so in the HYDRIDE paper, I think we talk about it a lot in detail. So we have a set of compiler transformations so that we do on the pseudocode to collapse the instructions. And so right now, at least it's kind of fixed. The sequence of transformations are fixed. So the ways the auto LVMIR get extracted are, they're not really exposed to the user, but I think it should be possible to kind of control how aggressively or how loosely you want to fold these classes.
Thanks.
Yeah. Do you hear me? Oh, yeah.
Yes, I can hear you.
Yeah, thank you for the great talk. The framework shows that it takes the input as the pseudocodes of various architectures, and I'm wondering, I'm wondering that where can I get those pseudocode, because it's a pseudocode and there is no real source code out there in the world, and
so all of these, so all of these are publicly available documentation. So for many architecture vendors actually do have some sort of public documentation of their semantics. So all the ISA semantics that we use, they're all available publicly. So Intel has it on, I think, a website called Intel Intrinsic Guide. ARM also has a website for these semantics, and Hexagon has a PDF with these semantics. So we had to write parsers for all of these documentations, but I think architecture vendors tend to provide these documentations to the public.
Okay, thank you.
Thank you.
Hi, thank you for your presentation. And I want to ask if your write rules consider the constants, because I see you abstract away the constants. And in some cases, the rule only valid if you for specific constant.
Yes, we do support rules which are based on constants. So, for example, multiplying by 2 is the same as left shift by 1. So those, then they don't get abstracted in that way. So the constant kind of remains, but basically in the case like that, it just becomes like the other parameters get abstracted, like the element type or the vector size.
So how do you differentiate these parameters? Like, how do you know this constant is used for vector or something, or how do you know this constant is used for the semantic of this rule?
I think we have a different. So it's a bit of an implementation detail which I can talk about offline, but we have a different representation for literals that differentiates between like literals in the parameters and literals as like data.
Oh, I see. Thank you.
All right, let's thank the speaker again.